Hello everyone and welcome to Lecture 4 of 124-104 Physics 1A. This lecture is titled Projectile Motion, but actually we will consider two kinds of motions, relative velocities and projectile motion. Previously, we learned about vectors and vector maths, and we said that the vectors are important when considering motion in two dimensions. So in this lecture, we will look at projectile motion as an example of two-dimensional motion, as well as relative velocities as two-dimensional motion. The key idea behind vectors when being used in two dimensions, as we have learned previously, is that if you have a diagonal vector given by a direction indicated by the angle theta, you can always break down this vector into its x and y components, and you then work with the x and y components as well as this original diagonal vector. Now, to start off, the relativity principle says that the laws of physics are the same in all non-accelerating frames of reference. However, velocity is relative. Okay? It depends entirely on the frame of reference. For example, if you want to determine how fast you are moving right now, the answer depends on which frame of reference you're looking at. It depends on whether you're looking at your movement or your speed of your movement compared to the room that you're in which case if you're just sitting down in your room as you're listening to this lecture, then you are stationary, your speed is 0. But even if you're sitting still on your desk or your chair at the moment, if you compare your speed to the center of the earth, then you are actually moving relative to the center of the earth. You're moving at about 1,300 kilometers per hour, depending on where you are located. Relative to the center of the earth. And then again, even if you are just sitting down motionless while you're listening to this lecture, if you compare your motion to the motion of the sun, because the earth is revolving around the sun, then you are effectively moving at a speed of about 30 kilometers per second. So this illustrates that velocity is relative. It depends entirely on the point of view where you are viewing your movement from. So the frame of reference, a very loose a very loose term that you can use for the frame of reference is the point of view. Right? So the frame of reference can include the position for which you are viewing an object from, or it can also include, for example, an imaginary stopwatch that can start at a specific time. We are free to choose any frame of reference we want, but a smart choice for frame of reference is one that simplifies the maths and allows us to calculate a problem in a more simple way. Okay. This slide illustrates some examples of frames of reference. We actually already encountered some of them in our first week's lecture. So for example, you have here a free-falling object. If you drop an object from a certain height, you are free to choose the reference for which you will set the y where y is equal to 0. So you can say that at this starting point where the ball was dropped, you can say that the initial height is equal to 0, in which case the final height will then be some negative value, because you used 0 as the reference height for when the ball was dropped. Of course, the ball falls vertically downwards, therefore the final height should be negative. Let's just say, to assign a numerical number, let's just say the ball dropped negative 0.5 meters below this initial 0 position that you have assigned. Alternatively, you can also assign that the final position is the 0 position. You can say that the ball dropped to the ground and you are assigning the ground to be at a 0 height. Therefore, the final height will be 0, and the initial height will therefore be some positive 0.5 meter value. Okay, so both choices of where you assign the 0 reference height is valid, but in your calculation you have to be consistent, so that if you chose this position to be your 0 height, then in your calculation you should put your final height to be negative 0.5. If you chose the ground to be your final height, 0 meters, then in your calculation you should then put your initial height to be a positive 0.5 meters. Right. So another example of arbitrary frame of reference is in choosing the convention for positive and negative directions, right? So as I've mentioned in the very first lecture, there's nothing stopping you from defining which is a positive or negative direction, but we are adopting the convention where moving to the right is positive, whereas moving to the left is negative. Okay. You can also choose the x and y axes. Okay. Conventionally, right, we draw the x and y axes as horizontal and vertical, and we have been doing this since the beginning of the lecture, where we said that the x-axis is along the horizontal and the y-axis is along the vertical. But there is also nothing stopping you from assigning x-axis to be tilted a little bit. The y-axis will always be perpendicular to the x-axis. This choice of orientation for the x and y axis we will find useful when we analyze, for example, an object sliding down an inclined plane, so that we assign the x-axis to be along the direction of motion parallel to the incline of the plane. We will look at more detailed example of this when we go to our lecture on forces. And a final example of arbitrariness of the frame of reference or point of view is choosing where to view the object from. So, for example, right, if you are riding a bus, or if you're in your car, for example, represented by this diagram here, you have a car that's moving along. If you drop a ball, okay, from the point of view of an observer inside the car or inside the moving vehicle, the ball, it appears as if the ball just falls straight down. And you can also test this, right? If you're riding a bus, you throw a ball upwards, it will appear as if the ball went vertically up and then vertically down back to you. But you can also view the motion from outside of the moving vehicle. If you view the motion from outside of the moving vehicle, you will see a different motion for the ball that was thrown inside the moving vehicle, because the vehicle is moving. The motion of the ball dropped inside the vehicle will have some component along the motion of the moving vehicle. So that's another example of, different, that you can give different answers to the same situation depending on where you are observing the situation from. Right, so here's an example of relative velocity. A falcon is flying due north at a constant speed of 13.9 meters per second, but the falcon is blown off course by wind, moving at a constant speed of 4.63 meters per second to the east. We want to calculate the ground speed and direction of the falcon, meaning from the point of view of a person on the ground who is observing the falcon's flight. How fast is the falcon moving, and in which direction is the falcon moving? Okay. Let's draw a diagram to visualize what's happening. Right, so you have this falcon that's moving, that's flying due north. Right, due north is vertically up. So you have this falcon that's moving due north, but there is wind that is blowing to the east. Right, so east is pointing straight to the right. Okay. Right, so you have this falcon, V falcon, that's represented by this vertical arrow pointing upwards, and you have the wind represented by V wind and drawn by this vector pointing to the right. Okay. Of course, from the point of view of the falcon, right, if you were the falcon and you were flying through the atmosphere, you would think that you are still flying straight, right? From your point of view as the falcon flying, it will appear as if you are still flying straight. But from the point of view of a person on the ground, okay, so let's say this is the point on the ground where the person is observing the flight of the falcon. What the person on the ground will observe will be this dotted red arrow, which is a combination of the falcon's flight as well as the effect of the wind that's blowing to the east. Okay? So effectively, the ground speed or the ground velocity observed by someone on the ground will be represented by this V ground vector, which will now be at an angle theta relative to the flight of the falcon, if we consider the effect of the wind blowing to the east. Right, we want to find the magnitude and direction of this V ground. We can see from this drawing it actually is the hypotenuse of this right angled triangle. It's as if V falcon is the Y component and V wind is the X component. So we can then calculate the ground velocity as the vector sum of the velocities of the falcon and the wind. Okay. Falcon is moving at 13.9 meters per second in the j hat direction. Okay. Recall the unit vectors. J hat is indicating that the falcon is moving along the y axis. And the wind is moving in the I hat direction, or the x x-axis. Right, the V ground represents the hypotenuse of this right-angled triangle. So from Pythagoras' theorem, you can also calculate the magnitude of the velocity of the falcon relative to the ground. That will give you the speed of motion of the falcon, 14.7 meters per second. And for the direction, you use the tangent theta. Tangent theta is opposite, which is v wind, divided by the adjacent side, which is v falcon. And that gives you an angle of 18.4 degrees. Another example is a boat moving on a flowing river. The boat's propulsion determines its velocity with respect to the water, and its velocity with respect to the observer on the shore is the sum of the velocity of the boat's propulsion plus the velocity of the river's current, right? So each of the variables are defined here. VBS is the velocity of the boat with respect to the shore, right? Meaning from an observer on the shore, it's what he or she observes as the velocity of the boat. VBW is the velocity of the boat with respect to the water. So this will be the velocity that the passengers in the boat observes, and VWS is the velocity of the water relative to the shore. It's usually where it follows the river's current. Right, so here's an example with numerical values. If the boat's speed in still water is 1.85 meters per second, okay, and if the boat is to travel directly across the river, just straight across with no motion up or downstream, and the current of the water is 1.2 meters per second, at what upstream angle must the boat head? In other words, right, the boat wants to travel straight across from one shore to another shore of the river, but there is current in the river that's flowing at that speed of 1.2 meters per second. In this illustration, it's flowing to the west or to the left. So for the boat to go straight across the river, the boat should travel at some angle theta, okay, so that even if the river's current will push the boat to the left, the effective motion of the boat will be going straight across the river. Okay, so that's what we want to find, is at what angle the boat should travel upstream in order to head directly straight across the river. Okay. So we write down what we know and what's given, right? The velocity of the water as observed on the shore is given as 1.2 meters per second. The velocity of the boat on the water is given as 1.85 meters per second, right? And what we want, the desired result, is for the boat to go straight across. Here, we want to find the angle theta. So theta is what we want to find. So notice how these three vectors form a right-angled triangle. Yeah, 90 degrees angle between VWS and VBS. What we want to find is the angle theta. we can use the trigonometric identity sine theta is equal to the side opposite the angle, in which case that is velocity of the water relative to the stream, divided by the hypotenuse, right? Sine theta, you have the mnemonic saw. Sine theta is equal to opposite side divided by the hypotenuse. The opposite side is VWS, hypotenuse is VBW, in which case it's just a matter of rearranging to find theta. So it will be the arc sine of 1.2 divided by 1.85 will give you an angle of 40.4 degrees. All right. Okay, here's another example for relative speed. So again, relative speed means the speed. It depends on where you are observing the object's motion. So in this particular example, you have two vehicles, a car and a truck. They approach each other. The car is moving at a velocity of 60 kilometers per hour to the right, as shown by the arrow here. The truck is traveling at 50 kilometers per hour to the left, and hence you have a negative sign here for the velocity of the truck, u. If they are 100 meters apart, how long before they meet? Right. If we choose the frame of reference in which the car is stationary, okay, so say you are the person in the car, it will appear like you are not moving, but the truck is moving towards you. That's so that the frame of reference in which the car is stationary. So in that case, the velocity in the frame of reference of the car will be 0. But the velocity in the frame of reference of the truck, the velocity v of the car in the frame of reference of the car will be 0, whereas the velocity u of the truck in the frame of reference of the car will be equal to the truck's velocity minus the car's velocity. So the truck's velocity is negative 50 kilometers per hour. Take away the velocity of the car, 60 kilometers per hour, gives you a velocity of negative 110 kilometers per hour in the frame of reference of the car. Right? That's kilometers per hour. We want to convert that to meters per second. As I've said in our very first lecture, the shortcut was if you divide that by 3.6, you can then convert kilometers per hour to meters per second. We want to find the time, how long before they meet, from the definition of displacement, definition of velocity, right? Velocity average is equal to displacement over time. The time is therefore equal to the displacement divided by the velocity. Right, we are still looking at the frame of reference in the car. Okay, so for someone sitting in the car looking at the truck is moving to the left, and therefore the displacement of the truck will be negative 100 meters divided by the velocity of the truck in the frame of reference of the car, which we solved to be negative 30.6. Hence, the time it takes for them to meet is 3.3 seconds. Right, as I've mentioned, the frame of reference is arbitrary, so we can also choose the frame of reference in which the truck is stationary, in which case we calculate the time before they meet from the point of view of a person in the truck. So the velocity in the frame of reference, velocity of the truck in the frame of reference of the truck will be 0 kilometers per hour. Right? It's as if the truck was not moving, but the velocity in the frame of velocity of the car in the frame of reference of the truck will be the sum of the two velocities of the moving vehicles. Um, right, so you have the 60 kilometers per hour velocity of the car, um, essentially plus, because you have minus negative 50 kilometers per hour, that effectively gives you a plus 50 kilometers per hour. So it's like if you're looking at the if you're in the frame of reference of the truck and you're watching the car approach you, it's as if it's as if you are stationary, but the car approaches you with a velocity equal to the sum of the velocities of the moving vehicles. So that will be 110 kilometers per hour. Again, divided by 3.6 to convert to meters per second, giving you the velocity of the car in the frame of reference of the truck to be 30.6 meters per second. And similarly, if you calculate for the time, you will arrive at the same time, 3.3 seconds. You can also answer this question by choosing the road as the original frame of reference, meaning it will be a person standing on the side of the road observing these two vehicles approach each other. And so from the frame of reference of this person on the road, this person will see that the car is moving to the right and the truck is moving to the left. So the velocity of the truck will be negative 50 kilometers per hour and the velocity of the car is 60 kilometers per hour. So the relative velocity from the point of view of this person from viewing from the road will be the 60 kilometers per hour to the right, okay, of the car minus the negative 50 kilometers per hour velocity of the truck moving to the left. You then again end up with 110 kilometers per hour or 30.6 meters per second, which then gives you the same time, 3.3 seconds for the two vehicles to meet. Right. So from those examples, we saw that the motion of an object really depends, the observation of how an object moves depends on where you are observing it from, right? If you were if you were riding a bus and you throw a ball straight up, you'll notice that the ball will go back down to your hand and you can catch it easily, right? So so from the point of view of yourself inside the moving vehicle, it's as if the ball only had a vertical component of motion. But from the point of view of a person on the ground, the person will actually see the ball moving up while at the same time seeing the ball moving along together with the moving vehicle. So the effective path that the ball will take will be this parabolic path here, which we call a projectile. Right. So now let's talk about projectile motion. Okay? How do we describe a projectile motion, and when will we have a projectile motion? Right. So first, let's consider motion along the horizontal. If, say, you throw a ball along the horizontal and we assume, let's just have this thought experiment where there is no gravity, so that the ball just goes straight horizontally without falling downwards. If the object travels at constant velocity, then it's easy to see that acceleration is zero, because acceleration is a change in velocity. And if the velocity is constant, then that means acceleration is zero. The velocity is constant only if the distance traveled is the same in equal times, right? So that if we look at this kinematic equation for delta x, then if the acceleration is equal to zero, this whole thing would be equal to zero, and the distance traveled will be equal to the initial velocity times the time. So at equal intervals, the object would have traveled the same distance in equal times. Right? Now, if we consider vertical motion due to gravity but with negligible resistance, we have free fall, the free fall that we learned in our previous lectures. If we look at the speed of the object starting from rest, we can figure that out using this kinematic equation. Starting from rest means that the initial velocity is equal to zero, and hence the final velocity at any point along the motion will be calculated using the negative gravitational acceleration. The negative is because the acceleration is always directed downwards, times the time for which you are looking at the final velocity. Okay. The distance covered by the object starting from rest and accelerating by gravitational acceleration during this free fall motion can also be calculated using the kinematic equation. Let's just change delta x to delta y to clarify that the object is moving along the vertical. Right, the object was dropped from rest, meaning initial velocity is equal to zero, hence the distance covered is calculated by negative 1/2 g delta t squared. If we then do this exercise and draw the positions of the drop ball at 1 second intervals, and we use this scale, so that we can draw it within the space of this slide. If we use the scale, 1 centimeter is equal to 5 meters. And just for simplicity, let's use gravitational acceleration rounded to 10 meters per second squared. If we want to find the position of the ball at regular time intervals, say at 1 second after the ball was dropped from rest, okay, time will be 1 second, times 10 will be 10, times 1/2 will be 5. So after 1 second, the ball would have traveled negative 5 meters below its starting point. Okay. Using the scale we used, 5 meters will be 1 centimeter. So if we draw the ball here, the ball would be located 1 centimeter below its starting point. Right? After 2 seconds, you have 2 squared is 4 times 10. 40 divided by 2 will be 20. So after 2 seconds, the ball would have traveled negative 20 meters. Okay, using our scale, that will be 4 centimeters, and the ball would be at this position. After 3 seconds, you do the same exercise. You find that the ball is now at 9 centimeters. After 4 seconds, the ball will be at 16 centimeters and it would have reached the ground. Now, this is just for the vertical motion without air resistance, right? This is for the free fall. Now, let's combine that with the horizontal motion that we've seen. So what if at every position, at every point in the horizontal motion, we turn on gravity? So say this is after 1 second, 2 seconds, 3 seconds, 4 seconds. So after 1 second, 1 second after the ball left the person's hand, the position of the ball horizontally is here. But then also if we turn on gravity, the ball would have fallen down to this position. Okay. After 2 seconds, the ball would be located at this position horizontally. But if we turn on gravity, the ball would have fallen down to this vertical position here. After 3 seconds, the ball would be in this position horizontally. But if we turn on gravity, the ball would have fallen down to this position, and we do that also for 4 seconds where the ball is now located, has now reached the ground. Okay. So if we trace out the path of the ball, we can see that it traces out a parabolic path, and this parabolic path is characteristic of projectile motion. So by looking at this example, we can see that projectile motion is actually a combination of horizontal and vertical motion, right? In the horizontal component, the same horizontal distance is traveled in equal times. Therefore, the horizontal component of velocity does not change. It's always the same. If you threw the ball horizontally with some initial horizontal velocity of say 2 meters per second, then at each point along the horizontal motion, the horizontal velocity will always be 2 meters per second, regardless of where the ball is horizontally. That means, therefore, that the acceleration along the horizontal will always be equal to 0. Always. Okay. For the vertical component, okay, because of gravitational pull, neglecting friction, the vertical positions become farther apart as the ball falls down. And that means that the object accelerates downwards due to gravity at a constant rate of 9.8 meters per second every second. Right. If we then look at it diagrammatically or schematically, the parabolic path is then due to the combination of horizontal and vertical components of motion, right? You have this horizontal component of motion where the acceleration along the horizontal is 0, plus the vertical motion where the acceleration along the vertical is equal to the gravitational acceleration that's always pointing downwards. If you combine those two motions, then you have this parabolic path that is called projectile motion. Right, so by separating the horizontal and vertical components, it lets us see that projectile motion actually consists of horizontal and vertical components. So the key idea will be to split the motion into horizontal and vertical components. So whenever you're dealing with projectile motion, you have to look at the horizontal component independently of the vertical component of motion. So say, for example, you have this ball and it is thrown at an initial velocity vi, so that it's at an angle theta relative to the horizontal, meaning your initial velocity is diagonal relative to the x-axis. So the key idea would be to break down this diagonal vector into its x component and its y component, right? So you have the x component of the initial velocity along the horizontal and the y component of the initial velocity, which is along the vertical. You then deal with these components separately or independently of each other. Right. So if we look at the motion along the horizontal, right, the kinematic equation for the final velocity can be simplified. We put the subscripts x, right, to remind ourselves that we are looking only at the horizontal component of projectile motion. Right, the horizontal component will have a constant velocity all the time, and therefore the acceleration is equal to 0. Right, we can then see that the horizontal component of the velocity will be the same regardless of where the object is. You can calculate the position of the objects along the horizontal at any instant of time, where delta x gives you the position. You know that along the horizontal, acceleration is always equal to 0. Again, the x's remind us, the subscript x's remind us that we are looking only at the horizontal component. The horizontal component of acceleration is always equal to 0, and therefore we can find the position by multiplying the horizontal velocity with the time. Right. Right. The total distance traveled in the x direction or along the horizontal is what we call the range. Okay, so when you encounter a problem that says calculate the range of the projectile, it's essentially asking you how far along did the object travel in the x direction or along the horizontal. Okay. If the projectile leaves and lands at the same height, which we set as y equals 0 meters, then the range of the projectile can be calculated by this equation here, where vi is the initial velocity, okay, and the angle is the angle of launch, angle for which, like say, this is angle theta, the angle for which the object was thrown relative to the horizontal axis. If you work out this equation, you will find that the range is maximum at 45 degrees, and the range is the same for complementary angles adding up to 90 degrees, right? So the range of a 75-degree angle projectile is the same as the range of a 15-degree angle projectile, right? And that's why for a 45-degree angle projectile, you'll have the maximum range. Now, if you look at the projectile motion along the vertical, okay, we're only looking along the vertical axis, the kinematic equation can then be written down with subscripts y, again to remind us that we're only looking at the vertical component. Along the along the y component, acceleration is constant, right? It's always equal to gravitational acceleration because the vertical motion is influenced by gravitational pull. So ay is equal to negative g, Okay. And this equation allows us to calculate for the velocity of the projectile along the y for any given instant of time. Okay. For its position along the y-axis, I can simplify that by changing a to gravitational acceleration negative g. Again, we put negative because gravitational acceleration is always pointing downwards. Likewise, the subscripts y indicate that we are looking only at the vertical component of motion. So we can use the same kinematic equations that we learned before, except that we separate the motion along the horizontal and the motion along the vertical axis. Right? The very first initial or crucial step to do is to separate the initial velocity into its x components and y components using trigonometry. Right? Right. Remember that the acceleration along the horizontal is always 0, while the acceleration along the vertical is always equal to negative g. And from those informations, you can modify the kinematic equations to determine the position of the object along the x, right? And the position of the object along the y. Right. The velocity of the object along the x is the same all the time, right? And the velocity of the object along the y will increase according to will change according to gravitational acceleration and the kinematic equation. All right, so how does projectile motion look like? Initially, you have this initial velocity that is diagonal. You break down that diagonal velocity vector into its x and y components. As the ball travels, it traces out this parabolic path, right? The x component of velocity is always the same. It's always equal to the initial x component of velocity regardless of where the ball is at during its projectile motion. Whereas the y component changes. If the ball initially was put into motion upwards, then we know that the velocity along the y will decrease at a rate of 9.8 meters per second every second until the ball reaches its maximum height, for which case when the ball starts to move down, the velocity will increase at a rate of 9.8 meters per second every second. There is symmetry about the maximum height, so that at equal heights, right? So at equal heights, notice how the magnitude of the velocity along the vertical component is the same, right? Only the direction is opposite. Right. For accelerations, because the velocity along the horizontal is constant, the acceleration should always be 0 along the horizontal component. Whereas for the vertical component, the acceleration is always equal to gravitational acceleration 9.8 meters per second squared, and it's always directed downwards. Right, so the key idea, I cannot emphasize this a lot because once you have grasped this idea of treating the x and y components separately and solving kinematic equations independently for the x and y components, it really simplifies the analysis of projectile motion, right? Most of the time, I see students confused with projectile motion because they mix horizontal components with vertical components, right? Whereas the key idea is to separate the x and y components and solve them independently. And that's why the very first step is to find the x components of the projectile and the y component of the projectile. And then you simply use the kinematic equations according to the motion along the x and y. So notice again, you're separating motion along the horizontal and motion along the vertical. And of course, there are special relationships that allows you to easily simplify kinematic equations, like acceleration is always 0 along the horizontal, acceleration is always negative 9.8 meters per second squared along the vertical. Okay. At ground level, we usually use ground level as the 0 reference point so that the position y will be 0. Okay. Time going up equals time going down. As I've pointed out, there's symmetry about the maximum height reached by the projectile, so that the time it takes to go up of the maximum height is equal to the time it takes to go down to the original initial height. And to find the maximum height, which we also used in calculating problems on free fall, to find the maximum height, we set the final velocity along the y component to be 0. All right, so let's just end this lecture with an example, okay, to see how to deal with projectile motion. So you have here a movie stunt rider on a motorcycle who speeds horizontally off a 50-meter high cliff. So as you can see in this illustration here, the cliff is 50 meters high. That's the vertical distance of the cliff. How fast must the motorcycle be to land 90 meters away from the base of the cliff on ground level? So as you can see in this figure here, 90 meters is the horizontal distance or the range of the projectile motion. So you have two distances here, one vertical, 50 meters, and one horizontal, 90 meters, which is also the range. Right. So we want to find how fast must the motorcycle be to land, right? So that means we are looking for VI. But let's write down what's given in the problem, and hopefully that will make it clearer. Okay, when you write down what's given in the problem, I recommend that you separate what's given along the horizontal, okay, and what is given along the vertical. Right? So it sets up your mind to separate horizontal and vertical components and work with them independently of each other. Right? So we've already mentioned that along the horizontal, the range is 90 meters. Okay. Along the vertical, the distance is negative 50 meters, because it tells, the problem specifically tells us that when the motorcycle reaches the ground, y is equal to negative 50 meters. Right. We want to find the initial velocity along the x, or along the horizontal, We don't know that, but what we know is that the final velocity along the x is equal to the final velocity along the y. The final velocity along the x is equal to the initial velocity along the x, because we know that along the horizontal the velocity does not change, and therefore the acceleration along the x along the horizontal is always 0. For the vertical motion, right, the motorcycle is just moving, speeds horizontally. The problem says that the motorcycle speeds horizontally, which means that the initial velocity along the y would be 0. Okay. The final velocity along the y, right, is something we don't know, right? So at this point, the initial velocity along the y is equal to 0. But as we've seen in the diagram for projectile motion, the velocity along the y actually increases. The velocity along the y actually increases as your object goes down, right? So this is the final velocity after the motorcycle hits the ground. So the final velocity, it's not 0, but the final velocity along the y is something we don't know, right? It's unknown. It's not given as well. But what we know is that the acceleration along the y is always equal to negative 9.8 meters per second. Negative 9.8 meters per second squared. Right. So we've written down what's given. We separated what's along the horizontal and what's along the vertical. Right. So what we were being asked is how fast the motorcycle must be. So if you're looking here, the motorcycle only speeds horizontally. So should we use the horizontal component or the vertical component to find how fast? Right? So the motorcycle speeds horizontally. So that sort of gives us an idea that we have to find Vix. What's the initial horizontal velocity of the motorcycle? But we do not know. Right, we do not know what is Vf, like here. So we cannot use any of these equations that has Vf. We only can use this single equation here. So if we use that equation, delta x is equal to Vix delta t plus 1/2 ax delta t squared. Well, we know that ax is always equal to 0. So this whole thing is equal to 0. So delta x is equal to Vix times delta t. Rearrange this equation to find Vix. Just erase that thing. So we want Vix will be delta x over delta t. Okay, which means that we need to find delta t to find Vix. So how do we find delta t? Delta t is the only common variable for the x and y components, right? Because the time it takes for the motorcycle to cover this 90-meter horizontal distance is the same time it takes for the motorcycle to cover this 50-meter vertical distance. So we can use the vertical motion to solve delta t. Okay. Right, so if we use the vertical motion to solve delta t, we do not know the final vertical velocity. Hence, these three kinematic equations cannot be used because we don't know the final vertical velocities. Hence, this is the only equation we can use to find the time. So that will be delta y is equal to VIY delta t minus 1/2 g delta t squared, right? And in our given here, we said that the initial velocity along the y is equal to 0, so that's 0 minus 1/2 g delta t squared. Right, rearranging this equation, delta t will be equal to the square root of negative 2 delta y over g. Right. If you plug in the numbers, you have negative 2, right? You have 50 meters for the distance along the y, and g is you have negative 50 meters as the problem shows, and g is 9.8 meters per second squared. Alright, we just use the number 9.8 here because the negative sign was already incorporated in the equation here. So if you put negative 9.8 here, it sort of cancels out this negative sign that you assigned for the g here being negative. So you'll have delta t, or the time that you'll solve, is 3.19 seconds. Okay. Right, you then use this time in this equation to find Vx, right? So you have there, therefore, Vix is equal to delta x over delta t, right? We're looking at the horizontal displacement, 90 meters divided by 3.19 gives you a Vix of 28.2 meters per second. Right. Okay. All right, so that ends our lecture on projectile motion. Again, the key idea is to separate the horizontal and vertical components and treat them separately, solve the kinematic equations along the horizontal independently of the kinematic equations along the vertical. We also learned that the velocity of the object in one frame of reference can be different from another frame of reference depending on, who is where the observer is located. And so the choice of frame of reference is arbitrary, But a good choice will be to choose the frame of reference that simplifies the maths. And we looked at several examples for different frames of references. So this ends lecture 4 on projectile motion. I'll see you next time.